If we wanted to create an experimental apparatus, I really can only share this experimental apparatus with you as a photo because, surprise, surprise, they won't let me connect car batteries to open live wires and short the circuit. But if you do find yourself in this situation, I won't say you should try it out. But if you do see somebody do this, you'll be like, that's why it happens, okay? So if you take a car battery, when I was a boy, the teacher did this. And these days they frown on it, okay? But if you take a car battery and you run a wire off the car battery through a switch, now this switch is like shockingly dangerous because it doesn't have any housing at all. But anyway, you run it through a switch, you're going to really make the sparks fly, actually. And he screamed for dramatic effect, I assume. And then you run the wire up through a retort stand and you string the wire across two retort stands. Now, if that wire actually splits, can you imagine like you split the wire or you twist together two wires so that they're side by side? The current's going to flow. Let's just say that this is the positive terminal and this is the negative terminal of that car battery. The current's going to flow and it'll go in the same direction. And so what we were talking about previously is what would happen if two current carrying wires were going in the same direction. You guys know the answer. Attract or repel? They'd attract, yeah. They'd slap together. And so you could actually turn this thing on and off. And you may be lucky enough to have like a lab technician in your first year university course that sets this kind of thing up for you. And the wires will clap with one another as you turn them on and off. That's kind of neat. I mentioned already, but this is the same idea that comes up for why our solenoids contract when DC current goes through. Now, if you send DC current through a solenoid, DC means direct current. So when I say DC current, it's actually redundant on the C. But DC current is current that just flows one way all the time. And that's actually what this electrochemical cell does up above. It just causes current to go one way all the time. But when we talk about our electrical power grid causes current to flow AC. Has to do with the way things are set up, and maybe I'll talk about that later, but for now I'll just say that it's AC, and it alternates direction 60 times per second, or 60 hertz in North America, and that's why we have a 60 hertz hum I mentioned earlier on our green boxes or our power transformers in our neighborhoods. But the current's going to be going one way and then back the other way. In this picture here, it is hard to see the three-dimensionality of this, but this is meant to be like a garden hose style diagram where the current's going away from us on the top. Sorry, not away from us, towards us on the top and away from us on the bottom as the coil wraps around. Now, one way I can tell that by investigating this diagram is by looking at the magnetic field orientations around the individual wires as they come towards us or recede away from us. Another way that I could look at this and figure out what's going on is to say, hey, if the current's going towards us, then on the top, that is, my fingers would be pointing towards you. My right hand fingers would be pointing towards you on the top. And notice my fingers would be wrapping around and going away from you on the bottom. That would mean that to the right on this solenoid is the north end. And when I inspect the magnetic fields again, notice that the magnetic field is spewing out of the right-hand side of the solenoid. So yeah, this is definitely the north end. This is the south end. See the fields orienting inwards into the solenoid. And so whether I'm investigating magnetic fields around individual wires or the magnetic field as a whole, I can figure out what direction current is flowing, right? So as I think about this, I think, hey, this solenoid has a length to it. And as I count it, I guess I could question how I should count it, whether I should count that there are 5 coils or 4. I think that I would choose to think of it as 4 complete coils. Can you see what I'm talking about here? So I would say that there are N equals 4 complete coils. And there's a length of solenoid here. Now, the reason I mention length and number of coils is that if I think about this spring as the solenoid, you know that if I stretch it, the number of coils per length is going to be less than if I let it be compressed. And so the design of the solenoid actually comes into play here in terms of how strong the magnetic field is going to be inside of that solenoid. And so I've got some remembering to do. One remembering is that the things that affect the force, and of course that means the magnetic field, is the current going through that solenoid. Also, the length of wire that lays parallel. So in this case, the amount of wire that's coiled up against each other. and also the distance between the wires. So that's going to have to do with the coil density, how many coils there are per linear meter or whatever, however you want to measure the length. Now I also have some equations. So I want to think about these equations. The magnetic field near a wire is equal to K times I1 over R. The K value, maybe I would give that to you as a magnetic constant, okay? But this would be, if I had a current, this would be our I value. The R value is how far away I am from that current. And I would be talking about what the magnetic field is along a contour of space at that distance away from the wire. This next equation is actually about solenoids, where we have the magnetic permeability of free space, which I would tell you, I would just give you that as a constant. This is magnetic permeability of a vacuum. And then I have N, which is number of loops. I is the current. And L is the length of the solenoid. Okay, and mu naught is the magnetic permeability of free space, the magnetic permeability of a vacuum, which has to do with how capable it is, or how capable that volume, that space is, of allowing a magnetic field to permeate into it. Okay, and so that would be a constant for particular material, but mu naught specifically is for a vacuum. Now this third equation, and I'll tell you, the way that we're going to use these equations is very much in like a plug and play, not like a systems of equation kind of approach. We're going to deal with them as like, hey, could you calculate the magnetic field near this wire or what have you, right? But this third equation is actually the first equation, but dressed up differently. Notice that there's an I1 in the numerator and R in the denominator, and then there's a mu naught and a 2 pi. What that means is that K must be equal to mu naught over 2 pi. See how mu naught over 2 pi. And earlier people were talking about, 2 pi radians in a circle. Everybody was really excited about that. Remember how we were all excited about that earlier in a conversation about math class? I was excited. I was really excited about that. So the thing that I notice is, isn't this a circle, this red line? And so somehow mu naught times I is spread out over 2 pi r. See how that's the circumference of a circle? It's actually just calculus. We're talking about something being spread out over the surface of a circle. Actually, the surface of a cylinder, if I'm being honest about it, right? But a circle, it's being spread out over a circle uniformly. And so this idea of 2 pi radians and going around circles is something that shows up in physics too. It's just sort of embedded in the calculus of where this formula comes from. And we're almost there, right? Like in terms of our math skills, I guarantee first year university, first year engineering, you're embedding that in your calculations. We're just not quite there yet. We can't do the calculus and the physics at the same time just yet. Yep. We're counting how many loops there are. So I'm going to cover up one of them. We're talking about how many complete loops there are. So there's like, if there's an out, yeah, because it means that if I have an away from you and a towards you, I'm going to count that as one loop. Yeah. I mean, if I'm looking at coils on a spring, oh my gosh, this is going to take forever to count all these loops. And if I'm being more realistic and I'm looking at an actual solenoid for electrical purposes, this one's a demo one. So this one's even big. The one that you're going to find inside of your computer or your speakers or whatever is going to be even more of a monster than this to actually sit there and count the coils. And I had one student yesterday or the day before, you said you had to sit there and count how many coils there were from when you made a little radio. You had to wind it yourself.
Yeah, by myself. Yeah, and then when I tried to sand it, because it was a tunable radio and I could change the length of the conductor,
yeah,
I sanded it with a power tool and it split, so I did it again.
That's terrible. Okay, so she's saying she had to wind these coils herself, exactly 90 for her homemade radio to work, and then she had to sand off the insulation so that she could apply a slider that she could slide along those coils, because the slider on those now uninsulated coils allowed a contact to be there so that she could tune her radio. And if you don't know what all that's about, then maybe you should take electronics, because that's kind of a cool course, right? But it overlaps with what we're talking about completely, right? It's just that it's the practical. And so this is kind of the theory side of things. And no, we're not building a radio in this course. But yes, we're talking about the theory behind how that radio might work a little bit, right? And the inductance from the incoming electromagnetic waves is not something we've touched on yet. But still, I think it's a neat thing. And we should all take engineering courses and electronics courses. Now, this last equation is the force that actually I would even argue that I should call this the force of two, one acting on two, because it's the force due to magnetic field 1 acting on current 2. And this L value isn't even how far apart they are from each other. The L value is the length of wire, the length of parallel wire. And so when I think about the L value, I'm thinking about right now this L value right here for the length of parallel wire that's running next to each other. The magnetic field around wire 2 would be calculated using, if I wanted to call this equation 1 and equation 2, depending on if you knew mu naught or not, you could use this idea of having the magnetic field using equation 1 or 2. And then the I2, I suppose you could use an ammeter to measure the current, right? And so we could talk about the mutual attractive force between two wires, but we might just focus on the force that's being exerted on wire 2, for example. Okay. Yep.
So sorry, is there so there's a difference between like uppercase L and then the cursive L?
Oh, sorry. No, sorry. Here I'm writing uppercase L. This is the L that I'm talking about for the length of wire parallel to each other. This L is an L for the length of the solenoid. Honestly, there's not like a hard and fast rule about what uppercase and lowercase, but I should be consistent at least. You're right. Yeah. Now, the one thing that I'm dropping from this, because we've talked about magnetic force on current carrying wires, is the sine theta. There actually is a sine theta tacked on the end of this, but since I've made our wires be parallel, the theta value ends up being 90 degrees. We're not going to deal with wires that aren't parallel to each other. So, yeah. So since the theta value is 90 degrees, did I get that right? Yeah. We're going to forget about this because sine of 90 is 1. So we're just going to say that we're only dealing with parallel wires, okay?